Hi there. In the previous section, we discussed what's an algorithm and data structure, and we have learned different types of them. We have also answered the question of why they are important in computer science. So in this section, we will discuss about an important concept, which is Big O. Big O is the language and metric we use to describe efficiency of algorithms. Without understanding Big O notation, it's not possible to develop efficient algorithms. If you don't know when your algorithm gets faster or slower, you will struggle to judge your program performance. This concept basically gives you one way of describing how the time it takes to run your function grows as the size of input grows. Let's look at it in the next example. Imagine a scenario that you have a file on your hard drive and you need to send it to your friend. And we need to send this file as fast as possible. How should you send it? The first thing that comes in our mind is that to send it by email or FTP or some other source of electronic transfer. This is correct answer if the file size is small. It is faster than to take it to your friend physically. What if the file size is really large? Is it possible that it's faster to physically deliver it via plane? Yes, actually it is. 1 terabyte file could take more than 1 day to transfer it electronically. It would be much faster to just fly it across the country. If it is urgent, you might just want to do it. So as you can see, delivery method is changed based on the file size. This means in the first method, the time that is needed for the transfer of file increases as the size of file increases. On the other hand, in the second method, the time that is needed to transfer a file to a friend does not depend on the size of the file. It does not matter if we carry 1 terabyte file or 1 GB file, the time that is needed for air flight is constant. So in computer science, this is called time complexity. It's a way of showing how the runtime of function increases as the size of input increases. So if we come back our example of transferring a file to a friend, we can easily see that in terms of time complexity, electronic transfer increases linearly with the size of the file, but physical delivery is constant in any size. There are various types of runtimes such as ON, ON squared, or O to the power of n. For instance, to paint an area of W meters wide and H meters high, the runtime could be described as OWH. Some algorithms are faster when the input is small. However, they become slower when the input gets larger. It's very crucial that our programs run faster because they are not executed in supercomputers. If a mobile app users face slow performance from the app, they tend to quit and delete your app. Thus, a proper algorithm must be chosen for our development. Okay, in the last lecture, we have learned what is the analogy behind the big O notation. Now here, we will look at different notations that are used in academics to describe runtimes. But in the industry, people tend to use big O. To understand different notations that are used to measure the performance of algorithm, let's look at real-life example. Okay, let's say we want to buy a brand new car, and obviously we want to know more about the performance of car, which means that we are interested how many liters of petrol it takes to drive 100 miles. Now in case of a car, there is not a standard answer for this question. Even though in any car's manual, it might mention that it takes, for example, 70 liters of petrol for 100 miles, this information is not direct, because a car can perform differently based on the condition. This number can be different based on which condition you are driving the car. So if we drive the car in the city traffic, it's obvious that it takes more petrol to reach 100 miles than when we drive it on the highway. And there might be situation in which we drive a car in mixed condition, both traffic and highway. Let's imagine that it takes 20 liters to drive 100 miles in the city traffic and 10 liters on the highway and 15 liters in mixed condition. So here we see that the same car can perform differently based on the condition that we drive it. Similarly, algorithm can perform differently based on the condition that is given. We have three scenarios in case of measuring of any given algorithm. These are the best case, the worst case, and the average case. Let's say for an algorithm it takes 1 minute to execute in the worst case scenario. In the best case scenario, it takes just 5 seconds to execute, And finally, in the average case scenario, it takes 30 or 35 seconds to execute. So with the help of this three notation, we can define the best, the worst, and average case of algorithm. As an example, let's examine quicksort algorithm. Those who don't know what is quicksort algorithm, you don't need to worry about it because I will provide detailed information in sorting algorithm section about it. But now you just need to know that it's an algorithm that sorts an ordered list based on the selection of random number as a pivot number and swap greater values. Let's look at this example over here to make things very clear. The first operation in this unsorted list targets the entire sequence of numbers. And the number is chosen as a reference for sorting, which is called pivot. It is chosen at random. This time, for convenience, let's choose the rightmost number as the pivot. Here, in our case, which is 5. The next thing that we are going to do is to place left marker and the right marker. Left is on the leftmost number and right is on the rightmost number. Quicksort uses these markers to repeatedly perform runs of operations recursively. The left marker moves to the right in each step and compares the number with the pivot number and stops when it reaches a number that is greater or equal to the pivot number. In our case, it stopped in the first case because 6 is greater than 5, which is pivot number. Then the right marker starts to move to the left, and this time, when it reaches a number that is less than pivot, in our case it stops at 3, which is less than 5. When both left and right markers have stopped, the markers' numbers are swapped. In our case, 6 swapped with 3. So the operation repeats like this until all elements get sorted. So in the best scenario, all elements are equal and the passover through the list happens once. So in this case, time complexity will be On, because we are passing through all elements only once. And so if we have n elements in the list, our time complexity will be On. In the worst case, if we are unlucky, the pivot is repeatedly biggest element in the array, so the time complexity will be On squared. And in the average case, sometimes the pivot number will be very high and sometimes will be very low, but it will not happen over and over again. So in this case, time complexity will be On log n. Okay, hopefully this example makes it clear and you have understood all three cases. Now to express different scenarios of algorithm, there are three different big O notations. The first one is big O. It's a complexity that is going to be less or equal to the worst case. For example, if we want to sort 1000 numbers, big O measures the maximum time we need for this sorting. Let's say we need maximum 10 seconds to execute this algorithm. This means that the execution will never exceed 10 seconds. It can be 8 or 9 seconds, but it will never be more than 10 seconds in case of big O notation. Then the next notation is big omega. It's a complexity that is going to be at least more than the best case. It is different from the big O notation. Here, we measure the minimum time that we need to execute an algorithm. There might be cases that we want to know minimum time of algorithm execution, which means that if the best scenario for the execution of an algorithm is 2 seconds, in terms of big omega, it will never be less than 2 seconds. For example, if we want to sort 100 numbers, and we know that in the best case it takes 2 seconds, it will never be less than 2 seconds. Sometimes this information is useful for us. Now, in terms of big theta, it's a complexity that is within the bounds of worst and best cases. This means that if we have an algorithm with maximum execution time 10 seconds and minimum execution time 12 seconds, in terms of big theta, the average time will be 6 seconds for execution. Okay, let's look at a real example for these three notation. Let's imagine that we have an array of 1 million elements over here, and our goal is to find a given number within this array. If we want to search a number which is located at the end of this array, in our case which is 9, we basically check each element one by one until we find the element that we are looking for. In this case, we will visit all elements of this array. Let's say the time that we need to visit each element is 1 millisecond, so the time that we need to visit all of elements will be n multiplied with 1, where n is the number of elements in the array. Okay, how can we represent this searching process in terms of notations? So in terms of big O notation, it will be On. This means that the maximum time that we need to find any given number within this array is n. It will not be more than that. As shown here, to find the last number in the array, which is 9, it takes n multiplied with 1. So it will not be greater than O n. In terms of big omega, it will be omega 1. This means that the minimum time that is required for finding any given element is 1. It will not be less than 1 to find any given number within this array. In our case, it will never take less than 1 to find first element in this array. In terms of big eta, it will be eta n divided by 2. This is the average time that is needed to find any given number. This is because for finding different numbers, we need various units of time. So we need to take average of these numbers. We need to know all these three notations for academic purposes. But when it comes to the interviews, we only need big O notation. And that's all for this video, and hopefully you have understood three different types of big O notations. Alright, in the last video, we have learned three types of algorithm runtime notations, such as big O, big omega, and big eta. Now in this video, we will look at some examples of algorithm runtime complexities. There are many time complexities exist in the world of algorithms. Here we will look at the most commonly used complexities. Here's the list of complexities that we are going to discuss. The first one is O1, which is also called order of 1 or constant time complexity, which means that for any given input, the execution time will not change. It will remain constant. As an example, accessing a specific index within an array. It does not matter whether the array has 10 or 100 indices. Looking up a specific location of the array will take the same amount of time. Therefore, the function has a constant time lookup. Here, as you see, when we access first element of the array, it will take constant time. It doesn't matter if there are 100 or 1000 elements inside the array. If we look at the real example, imagine that we have a deck of cards, and I ask you to remove the first any card at random. So you could simply grab a card from the deck without having to search through the entire deck. This is very easy task and takes constant time, whatever card we grab. Because here we are selecting a random card, and it doesn't matter which card we select, it takes always constant time. This is an example of constant time complexity. Now the next time complexity is linear time complexity, which is written as ON. Here, time complexity will grow in direction proportion to the size of input data. The best practice is to try to keep our function running below or within this range of time complexity. But obviously, it won't be always possible. A good example for linear time complexity is looping through the array elements. Here we have sample Python code, which loops through elements of the array. As you see, lookup time is directly related to size of our input. In our case, our input is array. If the size of array increases, then the loop time will increase proportionally. In other words, the larger the input, the greater amount of time it takes to perform this function. Of course, if the array only had one element, then the function will have constant time lookup. Now if we go back to our deck of cards analogy, again, if we have a deck of cards and I want to select a specific card, let's say we want to select 10 hearts from this deck. In this case, you have to look through every card until you find that card. Sure, there is possibility that it will be the first card in the deck, but it's highly unlikely. Now think about if the deck of cards were filled with the hundreds of other cards, which are not 10 hearts, your search is directly related to how large deck of cards is. If we have 100 cards here, we have to look one by one inside these cards and to find specific card. So which means that the more cards we have here, the more time it will take to find out 10 hearts out of these cards. And this is an example of linear complexity. The third type complexity is order of log n, which is called logarithmic time complexity. This time complexity refers to an algorithm that runs in a proportionally to the logarithm of the input size. Let's see the code here. In this function, we are logging numbers until the array length is passed. However, we can see that our function only logging the numbers at certain level. Since we will be repeating a constant time lookup multiple parts of the array, our function will not have constant time lookup. It should be noted that since our function does not pass through every index in the array, it will not have linear time. By using the range function of Python here, we start from the first element until we reach the length of the array, and each step we visit every third element, not all of them. So in the resource section of this lecture, I've included a file which shows how range function works in Python. So if you are interested what is the parameters here, you can have a look in that documentation. So to make things more clear, let's continue with our example of deck of cards. Again, using our deck of cards analogy, let's say our cards ordered and split it into two parts. In the first part, we have diamonds and clubs, and in the second part, we have hearts and spades. Now, if I ask you to pull out 10 hearts, you could safely conclude that cards should be in the second part, here, over here. Furthermore, we know that cards should be only within the heart, so which means that we will look at this part. Since we will be searching for 10 hearts, we can safely assume that the bottom half of the deck is irrelevant. This part is irrelevant to us. And we know that this list is ordered. And we can divide list into two parts and compare the number here with the number that we are looking. In our case, the number is 7. If we compare 7 with 10, we see that 10 is greater than 7, which means that we will look at the right part of this list. So from here, we can again continue to divide this part, and we will compare 10 here, and we see that we find out the number that we are looking for. And you see that we find out the number that we are looking for. As you see, we didn't have to search through every card to find it, but it also was not as easy simply grabbing a random card. So we have searched not all elements, but some of them. So that's why this time complexity called logarithmic time complexity. Another example for this time complexity can be finding an element in a sorted array. Using binary search algorithms, we can achieve logarithmic time complexity, because in the binary search algorithm, we are looking for x in n element sorted array. Let's see this example. In this example, we are searching for 9 inside this array. We are dividing this array into two parts, and the middle number is 11. We compare 11 to 9. We see that 9 is smaller than 11, which means that we will look this part. And again, we are searching for 9 within this half array. Then here, we are again dividing this array into two parts. The middle point here is 8. So which means that we compare 9 to 8. We see that 9 is bigger than 8, which means that we will look at right side. On the right side, there is left only one number. We are comparing this number with the 9. We see that it's equal to 9, and we return 9. As you see here, in each step, we are dividing our array into two, and every time it's getting smaller and smaller. For example, if we start with 16 elements of array, in each step, it divides 2, which will be 8, then 4, then 2, then 1. So the total time is a matter of how many steps we can take until we reach 1. So the question is how many times we can multiply 1 by 2 to get n. So the equation will be like this. Thus, where the number of elements in the problem space gets halved each time, that time complexity is logarithmic time complexity. So let's continue with the next time complexity, which is quadratic time complexity. Quadratic time complexity represents an algorithm whose performance directly proportional to the square size of input dataset. It's like linear data structures, but here the time is increasing quadratic. Within our programs, this complexity will occur whenever we nest over multiple iterations. Here again we have a piece of Python code. This function is a great example of how easy it is to pass through an array twice using two loops. It's clear that in the first part, our function will be searching through the array at least once. And for each loop, from the first loop, we iterate same elements in the second loop. In doing so, we are passing over the same array twice with each search, producing a quadratic time complexity. Let's revisit our deck of cards again. Let's say you pick the first card in the deck, which is 3 club in our case. And we want to get all 3s inside this deck. To get this, we need to revisit our deck again. So we will revisit the deck until we get all 3s from the deck. Once we are sure that we got all 3s, we will continue to do it with the second number, which is 7 heart. And this will continue until we reach end of the deck. And every time we go back to the deck, the time will increase quadratically. And this is an example of quadratic time. The next time complexity is exponential time complexity. Exponential time complexity denotes an algorithm whose growth doubles with each addition to the input set. If you know any other exponential growth patterns, this works in much the same way. The time complexity starts off very shallow, rising at an ever increasing rate until the end. Fibonacci numbers are the great way to express exponential time complexity. Although there is a way to make the Fibonacci function have a shorter time complexity, for this case we will be using double recursive method to show how it has an exponential time complexity. Since the number of recursive calls is directly related to the input number, which is n in our case, it is easy to see that how this lookup time will quickly grow out of hand. If we have great number here, the time that we need will increase quickly. So now we have explained the most commonly used time complexities, and it's normal that you might not understand some terms in this lecture. You don't need to worry about this because we will cover them in detail in upcoming lectures. So you might be interested that why we are including such concepts here. So the answer is without this concept, we cannot explain different types of time complexities. Okay, let's see how these time complexities are depicted in the graphic and which ones are good for faster and efficient programs. Here we have all these complexities on the graph. Here on the x-axis we have elements, which is the input numbers, and on the y-axis we have operations. As we mentioned before, the best practice time complexities are below ON, as you see here. Here you can see below ON, which is linear time complexity, we have green color. As you can see from the graph, it's good, and then it goes to excellent. In excellent position, we have constant time complexity, which shows that the time that is needed to perform operations does not depend on input elements. As our inputs increase, the time that we need to do operation does not change. So the constant time complexity is the best case for an algorithm. So the next complexity in the graph is O log n, logarithmic time complexity. Here again we see that this time complexity is also desirable, which stays below ON. And from the graph you can see that it's in green. Then above linear time complexity we see that ON log n time complexity, which is bad according to this graphic. And as you can see from here on, we have very horrible cases as shown in the graph. As you can see in the red part of our graph, as input increases, the time that we need to execute any operation increases dramatically, which is very time consuming, and that's why in terms of big O complexity, these cases are horrible. With this, we come to the end of this video. Hopefully you understood the different types of time complexity and you have an idea of which is desirable for an algorithm. Alright, in the last lecture, we looked at various time complexities, but the time is not the only thing that matters in an algorithm. We might also care about the amount of memory or the space that is required by the algorithm. It's a parallel concept to time complexity. Space complexity is a measure of the amount of working storage an algorithm needs. That means how much memory in the worst case is needed at any point in the algorithm. As with time complexity, here also we're mostly concerned with how the space that is needed grows as the size of the input grows. For example, if we need to create an array size of n, or n space will be required. If we need a two-dimensional array of size n by n, or n squared space will be required. Okay, to make things clear, let's look at the two examples below. This is just a block of code which is summing up the number from a given number till 0 by calling recursive calls. So methods like these, which are calling themselves recursively, count in the space stack. So each calls adds a level to the stack in the memory. So if each calls add a level to the stack and takes actual memory, this means that we need ON memory space for this block of code. For example, if we call this function for n equal to 3, we see that in each call, it adds a level at the stack. It means it takes a memory in the stack. As the input size grows, the memory that we will need will grow. So for this block of code, space complexity is ON. On the other hand, there might be some cases that n calls do not require ON space. Let's look at second example. Here we have two different functions. In the second function, we are summing up two numbers. Then for any given number of n, we are calling this pair sum function inside loop. Due to the fact that n calls to pair some function do not exist simultaneously on the call stack, we only need O1 space complexity. Here, the function is not calling itself recursively. It is just called inside this loop function, and it's not adding any level to the stack. That's why it takes O1 space complexity. Okay, this is all for this lecture. Hopefully you understand that we need to take into account space complexity as well. Time is not the only concern in algorithm performance. So in this lecture, we will look at why do we need to drop constants and non-dominant terms in big O. Dropping constants and non-dominant terms means that we can easily eliminate some values from asymptotic analysis. This means that for O to n, we can eliminate 2 from here and write On. Here we are dropping 2 as a constant and making this On. Similarly, we can drop non-dominant terms as well. For example, for this expression, On squared plus n, we can drop n from here and make it On squared. Then the next expression is On plus log n. Here we are making On, because O log n is faster than On, so we are making the On. So we are taking On here, which includes log n in itself as well. And the next expression is this. Even such a complicated expression, we can make it like O 2 to the power of n. So you might be interested, why do we do this? Okay, let's look at the reasons why do we drop constants and non-dominant terms. The first reason is that it's very possible that On code is faster than O1 code for specific inputs. Big O just describes the rate of increase. So for this reason, we drop constants, which means that O to n is actually On. And the second reason is that we know that different computers with different architectures have different constant factors. A faster computer might be able to access memory faster than a slower computer. So faster computers will have a lower constant factor for memory access than slower computers. However, we are just interested in algorithm, not the hardware, when doing asymptotic analysis, so we ignore such factors. Also, slightly different algorithms with same basic idea and computational complexity might have slightly different constants. For example, for this expression, if a multiplication is slower than subtraction, then the first expression will have a lower constant than the second expression, because here subtraction is faster than multiplication. However, we are not interested in such factors, so we will ignore computational complexity of subtraction and multiplication. And the last one is, as n approaches infinity, constant figures are not really a big deal. This means that constant factors are very small in the face of arbitrarily large n. All in all, in asymptotic analysis, we ignore constant factors because it removes a lot of noise from hardware and small changes in algorithms that really are not important for analysis, and this makes algorithms easier to compare. Hopefully you understand why we need to drop constant and non-dominant terms from the algorithms. This makes our life easier to compare our algorithms without depending on the characteristics of computers and computational complexity of different operations. Now, one of the most frequently asked questions from the students is that, suppose we have an algorithm that has 2 steps. When do we multiply the runtimes and when do we add them? This is a common source of confusion for students, especially during interviews. To make it clear, let's examine these 2 cases in these code blocks. In the example on the left, we have 2 separate loops, which is looping through array A and array B. But on the right, we have 2 loops inside each other. In the example on the left, we do A chunks of work first, then B chunks of work. Therefore, total amount of work is OA plus B. On the other hand, in the example on the right, we do B chunks of work for each element in A. Therefore, the total amount of work is A multiplied with B. In other words, if your algorithm is in form do this, then when you are all done do that, then you add the runtimes. But if your algorithm is in the form do this for each time you do that, then you'll multiply the runtimes. Many students mix these conditions, and it's very easy to mess up this in an interview. So be careful about this. Alright, till this lecture in this section, we have learned different features and types of big O. Now in this lecture, we will look at how to measure the time complexity of codes using big O. To make our lives easier, I have created a list of rules which will help you when you analyze any code. In the resource section of this lecture, you can find a PDF version of these rules. Okay, let's look at what these rules are. In this list, the first rule is any assignment statements and if statements that are executed once regardless of size of the problem take complexity of 1. And the second rule says that a simple loop from 0 to n with no internal loops takes O(n) time complexity, which is linear time complexity. Then the third rule is a nested loop of same type takes quadratic time complexity, which means that if we have any loop inside another loop, it will take quadratic time complexity, which is O(n) squared. And the fourth rule is a loop in which controlling parameter is divided by 2 at each step takes logarithmic time complexity. And finally, when dealing in multiple statements, we just need to add them up. This set of rules will help us to examine any given code and measure the code. You should be warned that some declarations may include initializations and some of these may be complex enough to factor in the efficiency of algorithm. So these are the most common rules that you need when you analyze any given code. Okay, now let's rule them all in one example. So here we will look at an iterative algorithm in which we need to find the biggest number inside a given array. Let's imagine that we have an array which consists of million elements. A method to find the biggest number in a given array will be something like this in Python. Here the method takes this sample array as an input, and then we declare a variable and assign this variable the first element of this list. Then we create a loop which starts from the second element till the last element of array. And inside loop, we check if the current element's value is bigger than the biggest number, and then we assign that element's value to the biggest number. And then we continue to the next element of array and doing the same operations that is inside loop. And this loop continues until it reaches the last element. Once the loop terminates, we print out the biggest number. So this is a simple method which finds the biggest number in the array. And the question is how we can measure this method using big O. So we need to analyze each part of this code separately based on the rules that we provided here. And then we will add all of them. Okay, let's analyze this code. The first line here is assigning a value. So according to our first rule, the time complexity of assigning a value to a variable is O(1). Then we continue to the second line of this code. Here we created loop. So according to the second rule, loop takes linear time complexity, which means that here it takes O(n) time complexity. Then inside loop, we have if condition. And again, the first rule says that if statements take constant time complexity, and which means that if condition over here will take complexity of O(1). Then again, we have an assignment here. This will also take O(1) according to our first rule. Then finally, we have a print statement here, which takes constant time complexity as well. Now we need to sum up these complexities together. First, we will start from here. The sum of these two time complexity will give us O(1). Because when you sum up these, it will be 2 O(1). Then we can remove constant from here, and we will get O(1). Then we will sum up O(n) with O(1), and from here we will get O(n). Because from previous lectures, we know that we can drop non-dominant terms from a time complexity. So here O(1) is non-dominant term. The dominant term here is O(n). So the result from here we will get O(n). So at the end, we need to sum up these three time complexity here. So if we sum up these time complexities, we again remove non-dominant terms from here. We have two non-dominant terms here, which is O(1) over here and O(1) over here. So we are removing this one, we are getting O(n). So this is all for this lecture. Hopefully you understand the concept, and with the help of these rules, you can measure any given code. As I mentioned before, I have attached PDF version of these rules in this lecture's resources, so you can download it and print it out, and when you analyze any code, you can use these rules. Now in the last lecture, we have learned how can we measure any given code using 5 rules that we provided. Now we will look at how can we measure recursive algorithms. Here again, I'll use the previous example that we used to measure iterative code. So we need to find the biggest number in the array, but this time we will use recursive calls. So our function in Python will look like something like this. Here we create a function which takes an array as a parameter and the size of array. The first condition here is if the array size is 1, then we return the first element of the array. Otherwise, if that's not the case, we compare current element's value, which is the last element, with the value that is returned from the same function with n-1. To make it clear, let's explain this with a sample array which consists of 4 elements. Here we have an array of A which has 4 elements. So the size of array is 4. So if we run our function for this array, it will be something like this. Now it will go to first condition and check if n equals 1. We see that n is not equal to 1, so it's continued to the next expression over here. Here it will compare the last element in our array, 7, with the value that is returning from the same function with n-1, which is in our case 3. So this means that this function over here calls itself with a different parameter, which is the same array, and n will be 3. So in this case, this function also will go over here, check if n is equal to 1. We see that it's not equal to 1, it's 3. Then it will go to this expression. Here it will again check the last element of this array. In this case here it's not going to be 3, it will be 2, which means that we will compare 12 here with the value that we are returning with the function n-2, which means that when we call in this function, it calls itself with a different parameter, which is 3 minus 1. So it will be like this. Then again, this function goes here and check conditions over here. We see that n is not equal to 1. Then it will call itself with 2 minus 1. Then it's going to be like this. We are continuing this until we reach where n equals 1. So here we see that we reach the function where n equals 1. So in this case, this part of code will run and it will return first element from the array. In our case, first element is 11, so the return from this function will be 11. So as you see, if we have a return from this function, we can continue to this function here. Basically, what we are doing here, we are comparing this value with the value from the array which has index of 1, because here we will take 2 minus 1. So the return from this function will be like this. We are getting the value of a1 and comparing it with 11. So value of a1 here, which is second element in our array, is 4. We are comparing 4 with 11, and the maximum value between these two is 11. So if we have the return value from this function, we can continue to this function here. So the return value from this function will be, we are comparing a2, 3 minus 1 will be a2, with the value that we get from here. So from here we got 11. So what's a2 value? A2 value here, which is third element in our list, will be 12. So we compare 12 with 11. The maximum value between these two is 12. So if we have return value from this function, we can go here to this function. So in this function, we will compare a3, which is 7, with 12. So the maximum value from these two will be 12. And this is how recursive function works. Hopefully, with this simple sample, you understand the logic behind the recursive call. Now let's see how can we find the time complexity for this algorithm. When we find time complexity for recursive functions, we have a standard. Here we assume that if a function calls itself recursively, it takes an n time complexity. And inside this function, if condition will take constant time complexity, and the returning of first element will take also constant time operation. But the problem is, when we come to this expression, we don't know the time complexity of this expression. But initially, we assume that our function takes mn time complexity, which is n from this parameter. So if we put as a parameter n-1, the time complexity will become mn-1. From here, we understand that if we combine these two constant operations, it's going to be O1 here. So the time complexity of this function will be O1 plus mn-1. So from these time complexities, we can write an equation like this. Because here initially we assume that our function takes mn time complexity, and from the expressions here, we identified that these two conditions takes O1 and the last one takes mn minus 1 time complexity. So if we sum up these two, we will get mn. So the next step is we need to continue this until we reach where n equals to 1. So we can say that when our function takes a parameter n equals 1, the time complexity will be O1. Because here we are not going to this expression, we are just checking these two expressions. So the combination of these two expressions is O1. So which means that M1 will equal to O1. So the next step is we need to find a few more backward equations from n till 1. So for n minus 1, our equation will be like this. Mn minus 1 equals O1 plus Mn minus 1 minus 1. So if we continue the same logic for n minus 2, we will get expression like this. We can continue this until we reach M1. But before continuing to the end, let's find a logic behind this. So based on these conditions, we can calculate our first function, which is Mn. Based on these conditions, we can calculate Mn. If I just copy Mn from here to here, and I can write O1 as 1, so our main equation will be like this. So if I replace the value of Mn minus 1 from here to here, I will get something like this. And if I do some calculations on this, the final result will be like this. So our aim here is to get rid of Mn function from here. If we can get rid of this function, then it means that we can calculate what is Mn time complexity. So again here, I will replace Mn minus 1 with the expression from here. So it's going to be something like this. Then if you do some calculation, we will get 3 plus Mn minus 3. So if you look at this function carefully, we see that there is an iteration in each steps over here, which means that the first value gets increased by 1, and the value over here gets decreased by 1. So which means that we can write this function like this. Here, a starts from 1 till the n. So as I mentioned, in this calculation, our aim is to get rid of m function from here. So to do so, we need to equalize this to m1. So how can we do this? In this case, if we put m minus 1 instead of a here, we can make this mn minus a to m1. So let's do so. So if we do some calculations, we will get something like this. This n here means that we have time complexity of n. So this is how we are calculating time complexity of recursive algorithm. Hopefully you understood the concept over here. But there might be situations where function calls itself here twice in each step. So how can we calculate time complexity of this case? Okay, let's look at it in the next lecture. Now in the last lecture, we have looked at how to measure recursive algorithms. By examining this function over there, we have found that the time complexity for this function is On. Now in this lecture, we will look at a tricky recursive call, which calls itself twice. So here, we have a function which takes an integer as a parameter. In the first condition, we check if n is less or equal to 1, then we return 1. If n is greater than 1, then we call this function with n minus 1 twice and sum their return values. This function is similar to the function that we discussed in previous lecture, but the only difference here, this function here calls itself twice. Many people might think that if in case of previous function, the time complexity is On, where the function calls itself once, so here calling itself twice can make time complexity On squared. This assumption is completely incorrect. Rather than making assumptions, let's derive the runtime by walking through the code. Suppose we call this function for n equals 4. When we run this function with f4, it will call f3 twice. Then f3, each f3 will call this f2s twice, which makes it 4. Then these f2s, each of them will call f1 twice. And this will make 8. So how many calls are there in this tree? You don't need to count them, but if you do, you will get 15. So what does this number tell us? If you look at this tree over here, we see that the depth of tree is 4. This is the first level, then second, third, and fourth. Which means that for our function, for fn, the depth will be n. In this tree, each node has 2 children. f4 has 2 children of f3, and each f3 has 2 children of f1, f2, and each f2 has 2 children of f1. So here in the level 0, we have only one node. Then we are continuing to level 1. Here we have two nodes, 1, 2. Then in the level 2, we have 1, 2, 3, 4 nodes. Then in the level 4, we have 8 nodes, which means that we can express each level with the level to the power of 2, as you see in this table. So if we sum up these levels, we will get 15, which is the number of calls we count over here. So from math, we know that sum of powers of 2 is equal to 2 to the power of n plus 1 minus 1. But in our case, we are not going to till n. We are summing the powers till n minus 1 to the power of 2. So in this case, our equation will be like this. And if we eliminate from here the constant minus 1, we will get O n to the power of 2. So from here we can come to conclusion that when you have a recursive function that makes multiple calls, the runtime often will look like this, where the branches is the number of children in each node, which is the number of times each recursive calls branch. So in our case, the function calls itself twice, so our branch equals to 2. So we have identified that the depth equals to parameter of function, in our case, which is n. This means that for n parameter, the time complexity is n to the power of 2. So in this lecture, I try to explain you three key recursive call algorithm. Hopefully you understand everything. So in the next lecture, we will look at interview questions that are asked by famous companies about BIG O.